Our modern theory of gravity was discovered a little over a century ago with Albert Einstein's general theory of relativity. And then just a little under a century ago, we discovered quantum mechanics, which would become our modern theory of everything except gravity. It was an exciting decade or so for physics. But then things slowed down. We've spent the following 100 years trying to reconcile these two theories and bring them together into a single master theory of everything. The most common approach to this reconciliation has been to try to make gravity quantum. After all, we got a theory of quantum electromagnetism by quantizing the electromagnetic field. The result was quantum electrodynamics, in which the force of electromagnetism can be described by the exchange of a single quantum of this field, which turns out to be the photon. The same basic procedure led to the discovery and quantization of the strong and weak nuclear forces with their associated particles, gluons carrying the strong force and W and Z bosons carrying the weak. So if the four forces of nature are quantum, surely quantizing gravity is an essential step on the path to a final theory. And if the gravitational field is quantized, then it should be made up of quanta. Gravity should be mediated by its own force-carrying particle. We call this hypothetical particle the graviton. Detection of the graviton would allow us to confirm gravity's quantum nature and even test out theories of quantum gravity such as string theory and loop quantum gravity. The holy grail of theoretical physics is to come up with a quantum theory of gravity, but after a century of trying, we really have no idea how close we are or if it's even possible. But we shouldn't feel bad, because it turns out that the universe is doing everything in its power to make this as difficult as possible. Well, perhaps it's just telling us that quantum gravity isn't possible. Should we take the hint? We've talked about these theories in the past. They are mathematically very dense and involve quite a bit of speculation, and some have argued that we are getting way ahead of ourselves with these theories. So today, we're going to get right back to the basics. To do that, we'll follow some of the thinking of Freeman Dyson, who helped shape quantum theory from near the beginning and thought about the most fundamental questions for all his long life. We'll see what he had to say about whether it's even impossible to detect a graviton, something we need to do in order to verify that gravity really is quantum. But first, we're going to follow another musing of Dyson's, in which he asks whether the same trick that told us that electromagnetism must be a quantum force can also be applied to graviton. The quantum nature of electromagnetism was the very first clue that led to the quantum revolution. It first showed up in the mathematical trick that Max Planck used to explain thermal radiation. And this inspired Einstein to take the quantization of electromagnetism seriously in order to explain the photoelectric effect. We understand that the electromagnetic field and electromagnetic waves, aka light, can be described as being composed of countless tiny and individual packets of energy called photons. Planck and Einstein's discoveries were clues that led to the full development of quantum mechanics in the mid-1920s, which was followed quickly by our full quantum theory of electromagnetism, quantum electrodynamics. But even before electromagnetism was properly quantized, Niels Bohr and Leon Rosenfeld came up with a strong argument that this force must be fundamentally quantum. Maybe if it works for electromagnetism, we can also use it to argue for gravity being quantum. Let's start with a simple particle in motion. At any point in time, the particle has a position and a momentum. If this is a quantum particle, then it's impossible to simultaneously measure both of these properties with perfect precision. If we try to measure the position very precisely, then the uncertainty in the momentum increases. If we try to measure the momentum as perfectly as possible, then the position becomes undefined. And it's not just that we lost the certainty in one property by bumping it or whatever when we tried to, or the other. The Heisenberg uncertainty principle is a fundamental limit to the knowability of the quantum world, and we talk about this fundamental in this video. This trade-off between the knowledge we can possess about a quantum system applies to many pairs of properties: position versus momentum, energy versus time, one axis of polarization, or spin versus a perpendicular axis, and many more. So if the electromagnetic field is quantum in nature, then the Concy principle should apply to our attempts to measure this field. Okay, back to our particle. Let's have two particles and give them both a negative electric charge. We start them off moving towards each other. We know that light charges repel, so these particles will interact by the electromagnetic field when they get close and be deflected back. We know that there's a quantum restriction on how precisely we can measure the position and momentum of these particles. But we also know that the particles' motions are entirely defined by their interactions via the electromagnetic field. So Bohr and Rosnell argued that the same restrictions on measurement of particle motion have to apply to the field that governs that motion. After all, measurements of the electromagnetic field can only happen by observing its interactions. If those interactions are subject to fundamental quantum uncertainty, then the field must be also. And if that's true, then it's reasonable to think that the electromagnetic field is truly a quantum entity, as indeed it turns out to be. If this argument applies to electromagnetism, why can't it also apply to the gravitational field? If we can only measure the gravitational field through the interaction of massive particles, and those particles are subject to quantum uncertainty, then surely our measurement of gravity is subject to the same here. It's important to pay attention to the details of the Bohr-Rosenfeld argument. They realized that in order to confidently state that the Heisenberg uncertainty principle applies to electromagnetism, we need to consider only a pristine electromagnetic interaction between the two particles. The interaction needs to be mediated by the most quantum possible influence of the EM field, a so-called quantum of action. That's the part of the EM field that we're trying to measure. If there are any extra bits of electromagnetic field, then they'll add to our uncertainty in measuring the field responsible for the interaction. But electromagnetism is pretty messy. This is where we get stuck with gravity, more or less, which has another detailed explanation about it. Particles with electric charge are subject to the electromagnetic force. The analogous charge for gravity is mass. There is more to this theory, which we can come up in the next part of this video for you, so make sure that you subscribe to our channel and press the bell icon. Apart from that, what are your thoughts about this theory? Comment down below and share this video with your friends and family. Thank you for watching this video until the end.